Okay, cool. So my name is Jay Haridas, and I'm a senior development lead in Windows Azure Storage team. And obviously, I'll be talking about Windows Azure Storage because that's the only thing I know about. So before I start off, I just wanted to figure out how to pace this presentation because I have a hell of a lot of slides, and I have a lot of code to show. So what I wanted to know is how many of them are new to Windows Azure Storage? Cool. How many of you are developing on Windows Azure Storage for mobile, like Windows Phone? No, there, here. Awesome. Great. So obviously, I don't have any demos for the Windows Phone because it needs a lot of things to do. But I don't want to get into demos about how to use Windows Azure Storage. And if you're using the Windows Azure Storage client especially, are everyone familiar with the Windows Azure Storage client, especially folks who are building on the Windows mobile phone and things like that? So I wanted to kind of get into the pitfalls to what you need to be careful about and things like that. And I have some demo code showing some best practices. So that's something I would like to do today. I will start off with this basic about what is Windows Azure Storage. Blobs, tables, queues, drives. I'm going to go through it and show some demos, simple demos as to how you can upload blobs and how you can write to tables. And there are some advanced topics like how do I store multiple entities in table and things like that. So I'm going to go over those things. Partitioning and scalability. How many of you are developing out here where scalability is a critical requirement in your application scenario? Nice. So this is kind of an advanced topic, and I want to kind of spend the last 15 to 20 minutes on partitioning and scalability. We've done a lot of presentations on this, but any amount of presentation is not sufficient to kind of understand how to scale using Windows Azure Storage. And then, of course, I'll try to get into Q&A. Just in case I can't get into the Q&A, because, like I said, I have a hell of a lot of slides, which I'm trying to go through. But I should be at the booth for more questions, and I'll be glad to go over your scenarios and help you with the scenarios if you have any questions. So we can also do the Q&A out there. We can continue to do it out there. So let's start off with what is Windows Azure Storage. It's a cloud storage system that we built so that you can start storing your data, right, onto the cloud. So you can access it, and you can think about your application scenarios rather than thinking, how many SAN servers do I need to store petabytes of data? For my new application that I'm developing, how do I buy these servers? How many servers would I need? And you do all your projection and things like that and build your own data center to start storing. Rather than that, we take that pain away from you. And what we say is you can concentrate on your application scenarios and allow us to kind of provide you a scalable storage system which auto-scales depending on your traffic needs. So we have a system that load balances based on your traffic needs to your data. The data is durable. We store multiple replicas of your data, and it's stored in such a way that we can say it provides high availability. By that, what we mean is we store your multiple replicas in places such that a hardware failure or even certain network failures will not kind of get your system down. We can still provide high availability. So that's scalable, durable, and high availability, and that's how we kind of provide that through Windows Azure Storage. The next best thing for those IT pros out here is you pay as you go. It's a utility service. It depends. Like, for example, if you're building a service that needs petabytes of data, you now have an upfront cost if you're building your own storage system. Right? You need to buy your servers. You have a heavy cost upfront. Out here, what you could do is when you're launching your application, you're not sure how many users you're going to get. So you could start off by one storage account. The only thing that you need to take care of out here is saying, hey, there's a limit on a storage account, transaction limit, and capacity limit. As long as you hit those limits, you're good. So now what you can do is you can get your projections and then decide how many storage accounts do I need, and where do I place these storage accounts, because that mostly is going to be driven by where your customers are. We have a lot of geo-regions for you to kind of select when you're creating your account, and what we preferably say is keep your storage account very close to where your applications, your web applications are running in the cloud. The reason being that the cost within the data center for ingress and egress is not charged. One size does not fit all. So that's why different applications have different needs, and we've provided different abstractions. When you're dealing with files and metadata associated with that files, you can start using blobs. If you have legacy applications that are doing a lot of NTFS APIs to store the data, you can use drives. You can move your legacy applications using Windows Azure Drive, which is built over something called page blob, and I'll get into it in a little while. But drives is meant for that, because it gives you a durable drive to write to for your legacy applications. Tables provides you a NoSQL, massively scalable, structured storage system. And queues, it provides you a way of reliably delivering messages to components, so you can decouple your two components that need to communicate so that they don't depend on each other, because if one component goes down, you can still rely on your message being delivered when that component comes back up again. So just this introduction, I would kind of, once you are kind of aware of Windows Azure Storage, what do you need to do to use it? You need to create an account. So you go to the portal, and you can create a Windows Storage account. Once you've created your accounts, you can then start creating containers for your data abstraction. So if you're storing a blob, you'll create a container that hosts all your blobs. If you're dealing with structured storage, you create tables and store entities in it. And if you're dealing with queues, you create your queues, and you can add and get messages from the queues. You get 3 DNS names, which are basically C names to the exact geo-region that your data is going to be stored in. For blobs, it's called your account name.blob.co.windows.net. For tables, it was table.co.windows.net. And for queue, it is queue.co.windows.net. So let's get into blobs. So we said it's a highly scalable and durable cloud file system. By that we mean that once you create an account, there's no limit on how many containers you can have. You can create as many containers as you want. There's no limit on number of blobs that you can store in that container. You can store as many blobs as you want. The only limit that cloud storage system has is an per account limit, which is 100 terabytes in capacity. If you want to go beyond that capacity, you can create multiple storage accounts. We've come across various scenarios where, like for example, in the CAD, if you're doing any CAD-related data, is anyone dealing with CAD or CAE out here? Or if you're dealing with any files that you want to start storing, and you want to start storing some metadata with that, maybe who reviewed this file, or which version of this file. So you can associate up to 8K of metadata with your blob. And obviously, once you have your blob there, the most intriguing part is how do you share it? There are multiple sharing scenarios, and I actually have a dedicated slide for sharing and a code demo. But there are public containers, which is basically you give read access to everyone, and then you can start using shared access signatures, which are pre-authenticated URLs, and I'll go into depth in a while. You can always upload and download your blobs, and we give some nice ways of uploading your blob where you can do chunk uploads, and you can do it in parallel. And then for downloads, we provide you a lot of conditional headers, like if not modified and if match and things like that, where you can do your ETAC checks. And in addition, we allow range reads. So you can only get the portion of your blob that you're interested in when you're downloading. So let's go through this quick demo. Before I go through, and I wanted to show the major demo that I had, which is using blobs and tables. I'll just go through what the demo does. So basically, this demo is for, I want to start storing my pictures and movies into the cloud, and then decide whether I want to make it public or give certain people access to it, like using shared access signatures. So this is the basic demo. So I can start uploading files out here. Oh, sorry. Thank you. So if we go back, you can see this picture that I uploaded, right? So this is basic demo, and I'll go into the code details of it. So rather than showing the code which is used by this demo, I've kind of abstracted it out into its own samples piece so that we can go through what the code does. So how do you upload these blobs? And before we get into that, there are a few things that you would like to do is, some of these things are taken care of by the storage client library. I've set off expect 100 continue to false. This gives you good performance because while you're uploading, you don't get this expect 100 round trip that you pay for, especially if you're uploading from a different geo region or different outside the data center. You don't have to pay for this expect 100 kind of tax. I've set off use Nagel algorithm to off, and this is more useful when you're dealing with small blobs or small messages. It's more our table entities. It's really useful then because we have a blog post in our Azure Storage Team blog site, which deals with why nagging is kind of deterrent to your performance as such. And then the default connection limit. And this is one of the things, and again, I'm just going over this for people who are new. This is one of those things that we keep getting this saying that, hey, our performance kind of sucks when we're using tables or blobs or queue. Why is that? And my web application cannot get enough throughput. And one of the reasons is because the default connection limit by default is 2, which means you can only have outstanding 2 requests at a time. You might make as many requests as you want, but the default connection limit needs to be increased, and this can be set depending on your requirements. So once I have that, let's just go to the blob sample. I'm going to go through the upload and download demo. I've created my storage account, which needs a connection string. And the connection string has basically your account name and your key. Once you have that connection string, you can start creating a blob client. You get your container reference. For me, the container reference out here is basically the ticket container. This getting the reference in the storage client has not issued a request yet. And then you invoke create_if_not_exist to create this container. And this is just a helper method which says if I get a conflict back again, if this container already exists, just ignore that conflict error. And then to the interesting part of your demo. So I get the container reference back again out here. And I get a blob reference from the container reference. So I'm uploading a sample blob, which is called ticket.txt in a container called ticket. So there are too many tickets out here. But once I get the reference, all I need to do is I'm uploading a text, but there are overloads which take streams. So if you want to upload a file stream, you can do that. You just have to upload this text. And that's about it. And this is the URL that you can access your blob. By default, everything is authenticated. It's not shared. I'll go over the sharing scenario a little later. But let's see how do I download this blob. To download this blob, I get the container reference back again, get the blob reference, and all I have to do is download to text. And again, there's a download to stream, which downloads to a file stream. So it's as good as calling blob.upload stream or text, and it's as easy as blob.download text. So this is how you upload and download your blobs. So this is the easy part. I haven't gone into a lot of other details, but this is how you can, and if you see the content, it's got back. Right. So I'm going to stop out here. And get into, while uploading, what if I'm not uploading a simple text? That's easy. What if I'm uploading a huge, massive file, which is more than a gigabyte on a slow network connection, right? So if I'm uploading, let's say, gigabytes of files, like, how do I upload this now, right? Because in our storage client, the REST API, if you look at this REST API, it allows you to upload in one chunk if it is less than 64 MB. Greater than 64 MB, you need to use something called block upload if it is block blobs, and I'll get into the details again, or page writes, right? So you need to use those chunked writing schemes to kind of write these blobs. And one of the complaints that we usually get is my request times out. I just have this particular code. It used to work well when I was trying to upload. Ain't it simple? But when I have a huge, massive file, it times out. What's wrong? The default timeout, which it uses, is 90 seconds. If you're on a slow network connection and even uploading a 64 megabyte file on a slow network, it will time out in 90 seconds, especially if you're doing this from outside the data center, right? So what we prefer to do is give a timeout based on size-based. And you can give your own timeout out here. In blob request options, and I've just increased it to 3 minutes rather than just 90 seconds. So this is one of the things that you would have to do depending on the size of the file you're dealing with. So you need to change your timeout. The blob request option also has retry policies that you can set. And the retry policy can be set on the blob client itself rather than yep. This takes an encoding. Yeah. And that's all you need to do. And obviously, the process is still running. Right? So that's the thing where how you set your timeout. So we saw how to upload and download the blob, and we'll get back at the sharing scenarios out there. The third part was sharing. But it's very simple to upload and download your blobs, and that's what I wanted to get at, rather than dealing with a block blob or a page blob, because I've heard a lot of complaints saying that, why do I need to deal with these two different kinds of blobs, and which one should I use? So let's try to answer that particular question. There are two kinds of blobs, block blob and page blob. Block blob is targeted at streaming workloads. You can think of block blob as made up of 4 MB chunks, and it's a linked list of chunks. So you can upload these blocks one at a time or in parallel in any order you want. Each block has an ID associated with it. And once you have uploaded all the blocks, you issue a commit blob. It's when you commit, you decide what's the order of those blocks that you've uploaded. So you give the list of IDs, and that's how the blob will be formed on the storage server side. So basically, Yes. When you upload, but up to 64 megabytes, you can just upload the entire blob. Yes. When you're uploading more than 64 MB, the question was, are we doing a upload of linked list? Are we doing a block upload behind the scenes in the storage client library? And correct me if I'm wrong. So if you give more than 64 MB file size, then the storage client library is actually going to do a parallel upload of the blocks of 4 MB in size. But if it's within that 4 MB, and you can control that, on the blob client, you have two parameters where you can say, at what stage do I start doing block uploads? Like maybe I'm doing 20 MB upload on a slow connection, and I don't want to do a one sequence of upload. I want to break it into chunks so that it gives me this efficient retry. So you can go and set saying that I want to upload these blocks. I want to upload this blob as blocks when the size is 20 MB. By default, it is, I think, 32 MB in the storage client library, but you have the control. The old storage client library did not give it, but I think starting 1.3, we exposed that parameter where you can control this. There's a knob to turn this on. In addition, you can also decide what's the chunk size. If you prefer 1 MB chunks, you can set it to 1 MB. The max is 4 MB, but you can set it anywhere from 1 MB to 4 MB depending on your scenario. So basically, it's the two-phase commit. The two-phase commit is awesome for slow networks especially, so I can start uploading, and then I can resume my upload and things like that. So there are various scenarios you can start building on top of block uploads. And both the kinds of blobs allow you for range reads. So it's not anything specific to blob. Both the blobs allow you how to do range reads. The size limit on a blob, which may be a factor for your decision as to which blob I need to use, is 200 gigabytes. So I'm going to skim through this because this is what I was trying to say, that if I have blob that I need to upload, these blocks can be of any size. I give it a block ID, and I can upload it in any order. And if anything fails, I can just upload that particular block that failed and then call commit. And that's how your blob is formed. And now when you read, you don't have to read those chunks. You can read the entire file. You can read any ranges. Right? So let's move on to page blob. So page blob is targeted at random write workloads. By that I mean, if you want to write to a particular location, not insert, but write, overwrite the data, then you can give an offset and your page size or page data and write to that blob. Its size limit is 1 terabyte, and you can think of it as consisting of array of pages. Rather than a list of pages, it's an array of pages, which gives you random access, writes. Each page is 512 byte in size. Whenever you write to the page blob, you need to make sure that you're aligned at this 512 byte boundary, a multiple of 512 byte boundary. And the size has to, again, be a multiple of 512. We allow you to write up to 4 MB worth of pages in a single shot, so contiguous pages, 4 MB. But it has to be a multiple of 512. And again, range reads are possible. And when you create a page blob, you determine the size of your page blob. And when you write this page, it is committed. It's not a two-phase commit. It's committed right then. So when you create a page blob, you give it a size, and then when I start writing pages, this data is available. But let's assume I created 1 terabyte of a page blob, but I've just written one page, 512 bytes. The rest of the data is zeroed out. You can still get it, but it's zeroed out. And to allow efficient downloads, we provide you an API called getPageRanges, so you can get the range of pages that have valid data. So going through an animation to just show this in a picture, write 5K pages. So when I do a put page, I create a page blob, and let's say I did a put page for 5K. I can always clear the data at anywhere but it has to be a multiple of 512, so from 1024, and the amount of data that I'm clearing is again a multiple of 512. I can overwrite, or I can also truncate the blob once I've created it. So these are the options that are available to you in page blob. So moving to the sharing scenario. So like I said, every blob request must be authenticated. You need your secret key account name to access these blobs. However, for sharing scenarios, let's say you're developing the next social network which has no security. You just want it to be public. You can make it public so that everybody can read your blobs. But there are scenarios where you just don't want to make it public randomly. You want to kind of control whom you want to give access to. And there's something called shared access signatures for that. Shared access signatures are pre-authenticated URLs. And this allows you can share this pre-authenticated URL with people you want to share your blobs with. And I'll go with a demo which can explain this much better. There are two ways to do shared access control. And I'm only going to show you the recommended way. Our MSDN doc has the other way of doing shared access control too, or shared access signatures. So we've seen that we uploaded and downloaded the blob. Oh. Okay, that's good. So to give shared access signatures to people you want to share your blobs with, what you need to do is get your container. On the container, I can set permission. Out here, I've set permission. The public access is off. If I turned it on, then you didn't need your users to kind of authenticate. They could just access your blobs. And then I create something called shared access policy. The shared access policy has what kind of permissions do I want to give. So it has read, delete, list, none, which is no access. But I can allow even write access to certain people. So I can, right now I've selected to just give read access to the people I share the token with. And then I need to give an expiry time. I've said that the shared access will expire in 5 minutes. It could very well be 3 hours or days or whatever it is. But this policy has just 5 minutes of expiry. I haven't set the start time. You can also do this kind of scenario where you want to give access starting, let's say, in 2 days' time. So you can give a start time to it so that you can start sharing your blobs in 2 days. I haven't said anything, so by default, it's just going to start when the first request reaches. So the start time is basically UTC now. I give it a policy ID, and then on the container, I store that policy. So what this means is I've given access to all the blobs in this container. I've given read access to all the blobs. So I set the permission on that. And then I'm still the owner out here. I do a get shared access signature. I just need to create a new access policy. And I give the policy ID that I created and stored on the container. Once I have that, I can now print this token. And we can go through this demo now. I'll just execute this. I uploaded a blob. That's the blob name. And this is the token. And I'm going to show this in, whoops. So that's the token. If I go back again and take this particular blob and try to access it, I don't have permissions. This is anonymous access. I don't have permission. But let's assume that now I take this particular token with me, right, which says the resource is a container. The assigned identifier on the container is basically called share it. That's the policy ID that I had created. And then the signature was created using my secret key. So now that I've created this particular token, I go back here again. And access it. So now I have given this URL for an anonymous access because it's pre-authenticated. The reason I showed this recommended way of storing it on a container is because if I made a mistake, if I gave you delete access for something, or if I share it with the wrong set of folks, I can always go back and set the permission back again to none or whatever it is. I can remove that from the container because the policy is stored on the container. Right? So this gives me a way of revoking access, which is great. So the next topic is snapshots. Snapshots is this awesome, cool thing of versioning, right, where you can start creating versions. It's a point-in-time read-only copy of your blob. So when you create a snapshot, every time you create a snapshot, at that particular point in time, it takes a snapshot of your blob and keeps it as a copy, a read-only copy. You can read it, but you cannot write to it. And when you want to kind of go back to a particular version, you can always copy that snapshot as a blob and now revert it. You can basically copy it over your previous blob and say, hey, I want to revert back to a previous version. So that's what snapshot gives you. You can think of snapshot as versioning. You need to clean up your snapshots. There's no limit on how many snapshots you have at this time. So you need to clean up your snapshots. If you want to store 3 versions for your file or a blob, then you need to handle that and delete the previous snapshots, the old snapshots. What's really awesome about this is, so the question was whether you can download previous snapshots. Yes, you can download a previous snapshot, and every snapshot, and we'll go through this example out here, every snapshot has a unique ID, which you can use it to append it to your blob name and download it. And we'll go over that. And what's really awesome, which I was saying, is you're only charged for the unique blocks and pages. So if I create a file about, let's say, 100 gigabytes, and I take a snapshot, and I don't modify the base blob, I'm not charged for that snapshot, that version. But I still have a version with me. One of the pitfalls to remember out here is when you're using the storage client library, you need to use the APIs write pages and put block list. You need to use those APIs to update a blob. And I'll go over why exactly do we need to do that. So what does unique mean? I said you're charged only for unique blocks and pages. So let's assume I have a blob, and I have 2 blocks. I've named it ID1 and ID2. The content is A and BB. And the base blob is alphabets.txt. That's the name of the blob. When I take a snapshot, I get a read-only copy. And if you look at that snapshot equal to, it's a kind of a timestamp. We usually say treat it as a unique, though storage client actually gives you a date time. This is the name that you need to prepend to your blob as a query parameter. So alphabets.txt ? This is your address for that version. So this is the time which you see when the snapshot was taken. And what you're charged for is only the 2 blocks because they are unique. The snapshot is free. So I started off with 1 snapshot and a base blob. Let's assume I added the third block to the base blob. Now I'm charged for 3 blocks. Block ID 1, block ID 2, and the new block which I added. The snapshot blocks are still not charged for because they're still shared.
So your definition of unique, so I could have multiple snapshots, and there's still, it's just A and BB, but the data in them can change?
So I'm going to answer that question. Yeah.
You don't mean unique in that the data within it?
No, it's not the data, and that's, we can wait for the next slide, and that's what it shows as to what unique means. So this block ID, you can think of it as a pointer. So they're pointing to the same block at this point. If I take a snapshot, I'm still charged for 3 blocks. And I get a new snapshot with a new timestamp. So now let's go back to your question, which is it the data that makes it unique, or is it an ID that makes it unique? I'll rephrase your question, but let me know if that's not the right thing. So let's say I updated the block with the same data. It had A before, and I updated the block with the same absolute data, A again. Its block ID is still ID 1, and I commit the blob. And when committing the blob, I said use this new block which I just uploaded. Not the previous ID 1, but the new one. Now I'm charged for 4 blocks. The base blobs, ID 1, ID 2, ID 3. And now the snapshots, ID 1. When I updated that block, that pointer reference changed. So it's pointing to different blocks now. The data is the same, the ID is the same, but it's different blocks. And so now you're charged for these 4 blocks. If I take a snapshot now, I'm going to be charged still for the 4 blocks. So we don't do any dedupe on the server. We don't see, hey, is the data same, then I need to share it or anything of that sort. We don't look at the IDs. It's exactly what you upload. If you've done an upload block and overwritten something, that becomes a new block. Let it be the same data. So one of the things which I said in storage client, now if I use upload blob to actually upload A, BB, and CCC again, all the blocks are written, and now I'm charged for actually block the base blobs, 3 blocks, plus the snapshot, because all the blocks were overwritten. Yeah? Yeah? No. So your base blob is still a separate entity. When you change your base blob, the snapshot doesn't change. Your snapshot is a read-only snapshot. So when you change, the question was, is there a performance hit if I do a lot of writes to the base blob? Am I writing to the snapshots? No, the snapshot is a read-only version. It's kept as is. It's just that now we need to keep track of a new unique block that you've overwritten, and we just say, okay, that's a new pointer that I need to look at. So let's go quickly over the best practices. I'm running a little late, so I'll try to take the questions at the end if you don't mind. And again, like I said, I'll be at the booth, so I'll take all the questions at the end. Looks like I'm just going to be running a little late. So let me quickly go over the best practices. I mentioned about the timeout. Client library uses 90-second timeouts. I cannot repeat this enough times because we've got so many people who got kind of impacted by this particular timeout issue, where they're uploading this huge blob and it times out. So please set it based on your size. Use parallel upload. How do I get the best throughput? Rather than uploading just a single blob, if I'm on a slow connection, use parallel uploads, right? If I'm uploading too many blobs, you can upload these blobs in parallel. Or if I'm just uploading one blob, I can upload these blocks, and on a slow network connection, that'll be great. I mean, rather than each round trip, I'm uploading it in parallel and filling up the pipe. So snapshots, we went over it, use the block and page level APIs to update it rather than the upload blob or upload blob from text, stream, or whatever it is. The reason is because uniqueness is maintained when you do a block or a page level update. Shared access signature, we went through it. Use container access policy. The other one was basically where you keep all the parameters rather than keeping it on the container, that policy. You give all the parameters in the URL. The problem with that is you cannot revoke it once that URL is gone because there's nothing on the container, and whoever has access to that particular URL can get access to your blob. There's a 1 hour time limit when you try to use that second method on the expiry. So for 1 hour, anybody can access your blobs, and they can write, delete, depending on the permissions you're given. So use the container access policy so it allows you to revoke. And while sharing these are pre-authenticated URL, so share it as securely as possible. When you create new containers for kind of retention policy, for your logs, for example, which you want to retain for 30 days and then delete it, or 10 days and then delete it, try to create different containers. This will reduce your transaction cost. Rather than deleting each blob, which there could be a million of logs files, you delete the container. So that's a nice way of kind of reducing your transaction cost by creating a container for your retention policy and then deleting it. The container recreation, and yes, we have this nice feature where you need to wait for some time before you can recreate your container. The GC policy has to finish. We will be fixing this so that you don't have to wait today for the GC to finish, or rather, you don't have to wait for as long time as what you have to wait today. So we will be fixing it, but that's one of the things that you need to be aware of. If you are creating a container, deleting, and you want to recreate it immediately, you need to actually wait for some time before you can recreate your container. So if that's your scenario, try unique names or something of that sort to create your containers. So moving on to drives. I said that Drive provides a durable, Windows Azure Drive provides a durable drive for your applications to write to in the cloud. That's the important piece, in the cloud, right? So the Azure Drive is available for applications running on our virtual machines in the cloud, and it's a durable drive. The benefit of this is you might have a lot of legacy applications today, and I spoke to a few of you who are doing this, where you have your legacy applications, you want to just move it to the cloud. The easiest way is, rather than rewriting this application, it's using NTFS APIs today to store stuff. You move this today, and then load this Azure Drive, and you can still use your NTFS APIs to store to that drive, and it's made durable. So any flush write to that drive is made durable. The reason for that is Windows Azure Drive, that drive is a page blob, which is NTFS formatted VHD drive. So it's basically a page blob. So any writes to it is going to page blob. There's a driver sitting in a virtual machine which knows how to deal with it. It converts your NTFS APIs into these APIs to our page blob. It also has a cache which you have control over for read access. So it can start prefetching and caching so that it's really efficient and you can reduce your transaction costs rather than having no caching at all. So your legacy application needs to kind of mount this drive. You'll create this drive, mount this drive, and now you can start using NTFS APIs because you have this drive letter to work with. But a page blob, which is the fixed VHD, can be mounted only by one VM at a time for read-write. Drives can be up to 1 terabyte in size because the page blob limit is 1 terabyte. So you can use this drive to now move your legacy applications, which can just start writing to it. And one of the things which I would like to mention out here is, how do we make sure that there's only one virtual machine that can load this? There's this new API, or it's not new anymore, called lease blob. So you can think of leases as locks. So if you have a scenario like master election process, where you have multiple roles come up and only one role can do some processing, you can start taking lease over blobs. When you take a lease on a blob, every operation to that blob, every write operation to that blob needs that lease. And only one person can acquire a lease. So you acquire a lease for a minute, and then you need to keep renewing your lease. And if your process dies, the next person who asked for the lease can get it. And this way you can have this master election process. That's what we use out here, and that's how only one virtual machine can upload it, because it acquires the lease on the page blob. So my favorite topic, Windows Azure tables. It's a NoSQL, massively scalable, structured storage system. So what does that mean? There's no schema associated with it. You can think of it as rows that are basically property bags. It has a few fixed columns that you need to deal with, which is partition key, row key, and timestamp. But other than that, rest of your custom properties are basically a property bag. Name, value pairs. And it's massively scalable. There's no limit on number of tables, and there's no limit on number of entities that can go into a table. The only limit is the account space capacity. We provided a familiar to use REST API. It's basically OData protocol. We got lazy and said, hey, why do we need to provide a new REST interface and make our users learn this all over again? Why not go with what this team, OData team, has done in Microsoft? So we went with this OData protocol. And if you're working with .NET, you have WCF Data Services.NET, so it's part of your .NET to access Azure storage tables. So let's see how simple it is to, and this time I should get this right. Looks like it needs a more. Okay, cool. So table demo, before I go over this demo, what this demo does, it's pretty lame. What this demo does is it has multiple states and cities within the states. I got lazy rather than typing it. I said, OK, let me take 3 common cities that are there in the 3 common states. And I just said Ohio, Michigan, Alabama, and the 3 common cities. And I want to, this application is now tracking the population in each of these cities, right? So let's look at what I need to do. First of all, I need to define a class, a plain old C# object. In this, I have the partition key, and I've commented this out. The reason is because I wanted to show that you don't have to derive from table service entity, but if you derive from table service entity, I could remove these 2 because table service entity has already defined it. But I just wanted to do everything from scratch. Why reuse this time? So I have defined partition key and row key out here. And then I track the population in that particular city. I have placed something called an internal. I've marked it internal so that it is not saved into the Azure table. Any public property is saved, but any internal private properties are not saved. So the state is nothing but the partition key, and the city is my row key. The partition key and row key together is your clustered index. For those database folks out here in this room, that is your clustered index, so you know how critical that is. That's your only clustered index that you get when using Azure Table, so you need to use it depending on your application scenario. Back to the demo. When I want to add rows, I'm going to create the storage account, going to get the table client, and when I have to add rows, what I do is I get the table service context. The table service context is basically a wrapper over data service context, which is WCF data services. It's a data context, which has retries in it. So it has this automatic retry capability in the table service context, and that's why I used it, rather than the plain old data service context, which does not retry an operation. And I'm populating, I'm saying every city has 1,000. This time I got lazy. So for each state, for each city, I create a new population city entity. I set the state as a partition key. I set the city as a row key. And I keep incrementing the population. This is the one which is adding the object. It has not sent a request yet over the wire, but it has added an object into the context. And this is the table name that I've used, which is, again, guess what, TechEd. So I create the TechEd table, and I'm adding an object to it. So I do this for each one, and at the end, I do the save changes, and this is when the request goes out on the wire. I've used continue on error, which means that I've added about 9 entities right now. What it's going to do on continue on error, remember, I've not used batch, but I've used continue on error. So what it's going to do is it's going to send 9 requests. This one save changes behind the scene is going to send 9 requests to the table service, 1 for each row. If I had used batch, it would have sent 1 request with 3 entities, because I've just added 3 entities out here. To use batch, all my entities need to have the same value of partition key. So I can only do it at the state level. I cannot do it across states, because my partition key has to be the same to use batch. And this is the one which shows entity group transaction, which is the batch. In this particular method, I'm just incrementing the population by 100, and I update the object, and I call save changes again. This is being done for the state of Ohio. So what I do out here is I query for all the entities where the partition key is Ohio, and update the population by 100. And then call save changes, so it sends 1 batch request. For querying the rows in a particular state, I've again used something called the cloud table query. This is, for people who have dealt with LINQ, this should not be anything different. I just have a LINQ query out here which says, from this table, select all the entities where my partition key has this particular value. I've used cloud table query rather than a data service query, which comes in .NET. The cloud table query is, again, a wrapper over data service query, which gives you retries. And it also gives you this handling of continuation tokens. When you're retrieving entities from Azure table, there are various reasons why we may give you a partial result with a continuation token, and you need to come back to the table service giving that continuation token to get the rest of your data set. And cloud table query does that for me. So I don't have to deal with continuation tokens in the sample. So I'm going to run this particular program, the simple table sample, compile it, and I keep forgetting to close this. So on my tables, I'm just using a cloud storage studio. There are many cloud storage studios out there. I've just selected one of the ones which I already had a license for. So I just inserted these entities now, these 9 entities. And the query returned me all the cities in state of Ohio with its population. So it's as simple as that to deal with simple entities. But the good thing about cloud storage table is also that you can store multiple types. It's a NoSQL database. It's a flexible schema. So how can you use it to your advantage? In a conventional database system, you might store 2 tables that have some related information with a foreign key constraint, and then you do joins and retrieve it. So how do I get the same capability out here? So when it's at a partition layer, you can now use Azure Table to store multiple entities of different schemas in the same table. And to show that, I'll run this advanced stuff. I'm just going to update. And go back to those tables. And let's take it advanced. So if you look at this, I have stored a state information which says how many cities are there in that state, and what is the total population of all those cities in that state. So this row represents the Alabama state. And then these represent cities in Alabama. So you look at the clustered index. For this one, I haven't set any row key. And for the rest of them, there's a row key set to the city name. What is the advantage of this? Generally, you would have done this in 2 tables. We have a state table which says, OK, this is it. And then you would do a stored procedure to just update this in a transaction, these 2 tables in a single transaction. What I've done here is kept the partition key same, the state name. And now I can update the population and the state row in one single batch command. And I get the transaction capability. It's all or nothing. If anything fails, I don't have to deal with this transaction inconsistencies where the state has been updated or the city has been updated, not the state row. So this is how I would use multiple schemas in the same table. So the best practices: clustered index, partition key, row key. You would use a structure. You would use your clustered index for price-zero queries in your conventional database systems. You would do the same out here. Use the clustered index while querying. Limit large scans. Large scans can be painful in terms of if I have to show, let's say, the list of users in my web page, and I have 1 million users. If I have to just scan everything and then show, it's going to be really painful for the user who's going to come to that page. It's better to kind of paginate it and just show 10 users at a time and limit your scans. So the query you send will still be a range query, but limit it in terms of, say, how many rows you want back in your page. Expect continuation tokens for anything other than that is doing a lookup on a clustered index. Your point query can throw exceptions if resource does not exist. And this is one more of those things that I've listed out here because a lot of complaints have come in saying that, hey, I never expected an exception if this row does not exist. I'm searching for something where the partition key is foo and row key is blah. And I wanted to just check if it exists, and if it does not, I wanted to insert it. And now it throws an exception. The reason is because the WCF data service.net sends this request, a 404 comes in, web exception is thrown automatically. However, WCF data services.net has provided you a flag, a knob to control this, saying ignore resource not found exceptions. For read-only scenarios, turn merge tracking off. So you saw the data service context. It actually is tracking all your entities that you're adding. And if this is a read-only scenario, you don't want it to be tracking out there. You might have your own data model which is tracking all these entities. So you can turn it off. It's needed only for updates and delete scenario because it captures something called the E tag, the timestamp value. So that's the only reason why you need to turn it on. If you're doing only read-only scenarios, not updating it, then you can turn it off. Entity group transaction, semantics, it has to have the same partition key, and it gives you a transactional semantic of all or nothing. You can use this to your benefit whenever you're trying to do bulk uploads, or your scenario needs a kind of transactional consistency between two updates. Do not reuse data service context across multiple logical operations. The reason is because data service context is going to keep track of those entities and those changes. So if I'm reusing the same context in multiple places, what's going to happen is if one, let's say, insert failed because it was already inserted, you get a conflict error. When you reuse that same context elsewhere, it's going to retry that insert back over again, and it's going to keep failing. So that's one of the things that you need to be careful about. So create new data service contexts. It's not expensive to create these new data service contexts at this point. Add object and attach to, again, can start throwing it exceptions. And I know I haven't covered quite a lot of these things in the interest of time, but add object, you're inserting an object. If you insert it twice, it can throw an exception because it's keeping track of your clustered index. Attach objects similarly. The reason is because there could already be an entity that has the same clustered index which is being tracked by WCF Data Services.net. So Windows Azure Queues. It's highly scalable, available message delivery system. A storage account can create as many queues as it wants, and access is provided via REST APIs. When you start storing your messages, it is 8 kilobytes in size. That's the limitation for a single message. And the default expiry is set to 7 days. When you want to process this message, we have this two-phase of processing. The first phase just gets the message. It doesn't delete it. It's not deleting the message. All you need to do is give an invisibility timeout with it. And this message is not going to be visible to anyone who's going to do a get. Once you process your message, you need to delete it. What's beneficial about this is it allows you to process this message even if the process that has, or a worker role which has retrieved this message fails, it still allows you to process this message. A simple queue demo, and I'm not going to run through this demo at this point because I want to get through the scalability part of it. But again, once you have an account, you create your queue client. Oh, thank you. So once I create the account, I get the queue client, get the queue reference, create it if it does not exist, and then I have these add messages. All I'm doing out here is adding an integer to a cloud message. And all the add messages is doing is it's putting a message into the queue. When I process this message, it gets a queue reference. I have this polling time out here, so I'm going to sleep between polls whenever I want to try to get the message, because it could be that I have no message in my queue. If there is a message, I'm expecting an integer as a message, so I try to pass it out. If it fails, it means it could be a poison message. Somebody may have inserted an incorrect message. So if this is my processing, and if I had not checked for this, that message would have never got deleted. It would keep reappearing. So what I do is, every message has this DQ count, which tells you how many times it was DQ'd. If I see that this message has been DQ'd more than 2 times, and it's not a valid message, I want to delete it. And post an alert, or I want to store the data in a table which says, hey, there's this message that I didn't understand. I'm going to delete it. Somebody needs to look at it. You have fetch attributes which sets up the count of the messages. So you can see how many messages is in your queue. Unfortunately, I'm not going to run this, but I'm going to post this demo on our website. But what this does is it allows you to process your messages. Going back to this. So the best practices, make message processing idempotent. The reason is because something could fail. And when you get this message, the message can reappear in your queue because that invisibility timeout is going to expire, and that message is going to be visible back again. Do not rely on the order. Invisibility time can deliver certain messages not necessary in your order. The message size is 8 kilobytes. If you need larger messages, you can start storing messages in a blob and then store a reference. And I think I spoke to you about you doing the same thing where you're placing the message in a blob and then putting the message, and your worker role can go and process the blob. Use the DQ count to detect poison messages, or if there's anything wrong with your DQing, your invisibility timeout maybe, because of which you couldn't delete the message. When you try to delete the message, what happens is if that message has been, let's say you gave a 20-second time invisibility time, but you processed it for about a minute. When you try to delete it, if somebody else has retrieved that message, you cannot delete that message. So DQ count can kind of indicate problems in your invisibility time. Maybe you need to increase your invisibility time. Use message count to dynamically increase or reduce worker roles that are processing it. We get this frequently saying, it's really expensive. I'm polling my queue. My 30 workers are polling my queue every second, and it's getting expensive. What we suggest is use one worker. Poll it every second. If you find that there's backlog on that approximate message count, if you find there's a backlog, you can use the management APIs, service management APIs, to spawn more worker roles. And then they can start processing. But if you use one worker role and you're polling every second, you're going to pay $2.67 per month, rather than having 30 workers, and less compute costs too. So that's a better way of kind of designing your queue. So I have about 7 minutes left, so I'm going to quickly go through partitioning and scalability. Know your scalability targets. Quite a few of you raised your hands when I said, are you looking at scalability as a critical requirement for your scenario? And if it is, you need to know what the scalability target is. A single blob partition can do up to 60 megabytes per second. A single queue or table partition can do up to 500 transactions, single entity or single message transactions per second. An account itself has an SLA of 3 nines. It has a capacity of 100 terabytes. And with respect to transaction, it can do up to 5,000 transactions per second. And bandwidth is 3 gigabits per second. Know these limits. And now, if you can think of your scenario and you do your projections, you'll know how many storage accounts you need, or you'll know how many partitions you'll need. How to scale beyond this? Multiple accounts, if you're hitting this account limit. If you're hitting the partition limit, multiple partitions. So what is this partition? I've been talking about this partition. So what defines this partition? So every object that we store has something called a partition key. All the objects that belong to the same type, which is blobs or rows or containers, every object of the same type, if it has the same value for partition key, we say it belongs to the same partition. So if you are creating multiple rows, and let's assume you give it the same value foo, all those entities belong to the same partition. It gives you locality. This is important because our system load balances based on this partition key or partition. It ensures that all the entities that have the same value for partition key will be served by a single server. I use the word served, not necessarily stored. and I'll give you more details about that. It is served by a single server. And it would load balance these partitions to meet your traffic needs. Whoops. So load balancing can take up to a few minutes to kick in. We're not going to kind of load balance on every spike, right? So it can take a few minutes to kick in. And once the load balancing kicks in and the partitions are now assigned to be served by a different server, it can take a few seconds for that partition to be available on a different server. There's no data transfer happening, by the way. It's just the assignment which is changing. During this load balancing, you can get server busies. And what we ask is you need to exponentially back off on server busies. If you hit the single partition limit, you will continuously see server busies. Intermittent server busies, you can handle it. And that's why I said that retry policy, which I mentioned before, is really useful. Because the context or the clients actually have a retry policy that they take care of for you. So let's look at a single cluster, what happens out there. So we have a VIP for our front ends. We have 3 VIPs for virtual IPs, basically. One for blob, one for table, and one for queue. When a request comes in, it hits the VIP, which is a load balancer. It goes to one of the front ends. The front end decides, hey, what partition are you trying to, what kind of object you're trying to access, and what partition are you trying to access, and it sends it to the right backend. These are the backends that have assignment. Underneath this backend is this distributed file system in which your data is stored. The backend has only assignment of serving this partition so that it can have these transaction semantics and ensure transaction semantics, basically. Each backend will serve multiple partitions. A single partition will be served by a single backend, but a backend can serve many partitions. And based on your traffic, different partitions can have different load. There's a master system monitoring these backends which says, hey, how are my servers doing? If there's a lot of load on one of the particular server, the master is going to detect it and then say, I need to offload these partitions so as to reduce the load and load balance this traffic. And reassign those partitions, complete partitions, not partial partitions, but complete partitions, to different servers. So that's how load balancing works, and that's why partition is your key. Partition is what is load balanced. And you have control on your partition. We really believe that you know your data set well, you know your traffic well. So we've given this control of deciding what is your partition to you. And we'll go over what a partition is in each of the abstractions. For a blob, it is the container name plus blob name. That's a single partition. So you can assume that every blob is its own partition, right? So there's not much thinking to do out there. Every blob is its own partition. And then there's snapshot. So every blob and its snapshot is a single partition, because the partition key is your blob name and the container name. So the container name plus blob name becomes your partition key, and that is why a snapshot and all its blobs, or rather a blob and all its snapshots, belong to a single partition. For table, it is the table name and the partition key value. So we had a column called partition key. So that's what gives you control. It is not bad to have a single partition. It is not bad to have every row in its own partition. Both are acceptable, depending on your traffic needs. If your traffic fits within a single partition limit, you can keep all your entities in a single partition. However, if you are designing for scale and you are going above that limit, then try to think of what my partition key value should be so as to get this distribution of load, so that Windows Azure Storage can take care of your load balancing, because it load balances partitions. For messages, it is the queue name. So every queue is a single partition. So all the messages that go to a single queue is a partition. Yes, which means now if you want to scale beyond a single partition, you need to create multiple queues. So you create multiple queues that processes it, and you can go in a round-robin fashion and get your messages and process your messages from that. We spoke about scalability targets. So we did our own scalability targets, and I've just published the table one out here. So I wanted to compare and drive home the point why multiple partitions are good. So I'm comparing single partition insert, single entity inserts versus multiple partition. I've used multiple VMs. I've used extra large VMs so that I have the full compute power to kind of send requests to Azure table. And I keep increasing the number of VMs, and this is what happens. For a single partition, I start around at 300-400 on a single VM. When I increase more VMs to send more requests, I can get up to 1,000. But I set a single partition limit as 500. We have the capacity to serve more, but it's a shared system, and if anything, if a server becomes overloaded, it's going to look at these partitions that are getting more requests than the limit, and then throttle them more heavily. So for a consistent experience, that's why I suggest saying that stay within these limits of a partition, though a single partition can do about 1,000 requests. On the other hand, flip side, you see the multiple partition, I can get up to about more than 6,000 requests per second. On a single table, single account, I can get up to 6,000 plus entities per second. Again, the account limit is 5,000. You need to stay within that limit, but our system is built to scale. So I want to drive home that point that our system is built to scale. And this is for gets. Again, the same story. Single partition has a limit. Multiple partition will scale. So that's the reason why you need to now design. If you're designing for scale, plan for multiple partitions, plan how you want to create that. So just a few takeaways. We provide various abstractions, blobs, tables, queues, and drives. Each one meets a different need. We provided a storage client library which is really easy to use for .NET. And that's the block site at the end where we have a lot of information. Any new feature requests or anything about how do I get billed and things like that are all covered out there. There's a nice topic about it, and that's why I didn't cover about billing. But there's a nice blog out there which says, how do you anticipate how much you need to pay? For those who are new to Azure, go ahead and get your PRAS and try Azure Storage and try the different components in Azure itself. That'll be great to kind of learn. So there's a 30-day free pass. A lot of resources out here, and the slide deck is going to go up. I'm almost out of time. I'm actually out of time. So, and please complete your evaluation. That'll really help me kind of improve too.